Hello, Vital Sign. Today I'd like to explore the areas of regular polygons by working through an interesting math problem, the shrinking sides problem. You start with an equilateral triangle with all sides of length 1. Then you add a side, but decrease the side lengths to 1/2. Next we'll go to a regular pentagon with sides of 1/3, a regular hexagon with sides of 1/4, a regular heptagon with sides of 1/5, and so on, where the sides of an n-gon are defined as 1 over n minus 2. Let's call this case A. In case B, we start with the same equilateral triangle, but half the side lengths with each additional side. So now we're talking about a square with sides of 1/2, a regular pentagon with sides of 1/4, a regular hexagon with sides of 1/8, and so on, where the sides of an n-gon are given by 1 over 2 to the power of n minus 3. The shrinking sides problem asks if the sum of the areas of all polygons in case A, in case B, or in both cases is convergent or divergent. Keep in mind that adding sides increases the areas while decreasing side lengths decreases the areas. Here you can see regular polygons with side lengths fixed at 1, increasing a number of sides from 3 to 100. Note how the 100-sided shape is much larger than the triangle, even though they both have side lengths of 1. The top row of shapes are the first 8 polygons from case A. The bottom row is the first 8 polygons from case B. Observe that there is a difference between the two cases, and this suggests that our answer might be different for case A than for case B. Here's how we'll solve this problem. First, we'll find the formula for the area of a regular polygon based on its side length and number of sides. Then we'll tweak it to find the areas of polygons in case A and case B. Next, we'll graph this formula as a function to help us make an educated guess. And finally, we'll use limits to find out whether the sums diverge or converge. Let's begin with the first step, finding a formula for the area of a regular polygon based on its side length and number of sides. I'd like us to derive this formula ourselves, using only basic geometric principles. The key to this formula is the method of constructing a regular polygon. Let me show you by constructing a regular pentagon. First, draw a circle. Now a pentagon has 5 sides and a circle has 360 degrees. So let's divide the number of degrees to go around a circle by the number of sides in our desired shape to get 360 divided by 5, or 72 degrees. Next, mark the points where the 72-degree angles meet the circle. Note how using angles of 360 over n degrees has the effect of giving us n points evenly spaced around the circle, which is crucial when we're building a regular polygon with n sides. Next, connect the points to each other, forming our regular pentagon. To assist us in finding the area of this regular pentagon, let's draw lines from each point on the pentagon to the center of the circle. Note how each of these triangles formed by drawing line segments from the points on our regular pentagon to the center of the circle are congruent and isosceles. I'll leave it to you to work it out as to why they are congruent triangles and why they are isosceles triangles. If we could only find the area of one of these triangles, we could multiply it by 5 to get the area of our pentagon. More generally, if we can find the area of one of these inner triangles in an n-gon, we can multiply that area by n to find the area of our regular n-gon. So how do we find the area of one of these isosceles triangles? Well, often when you find the area of a complicated shape, you do so by breaking it down into right triangles. How can we turn the question of finding the triangle area into one of finding the area of a right triangle? Well, we can draw a bisector through this 72-degree angle, creating 2 congruent right triangles. I encourage you to pause the video and think about why bisecting an isosceles triangle through its vertex angle forms 2 congruent right triangles. I'll show the proof at the end of the video. We now have 2 little right triangles that we can work with. Find the area of one, multiply it by 2, and we'll get the area of the larger isosceles triangle. So how do we find the area of one of these little triangles? Well, this is much easier. The area of a triangle is simply 1/2 base times height. I'd like you to think about side AB. This side is just half the side of our regular pentagon. If we represent the side of a regular pentagon as S, then AB is simply half of S, or S over 2. Next, I'd like you to think about the length of side BC. Feel free to pause and think about it. Well, this is where the right triangle comes in handy. From the perspective of this 36-degree angle, side BC is the adjacent side of our right triangle, whereas side AB is the opposite side of our right triangle. The trigonometric ratio of cotangent, which by definition is the ratio of the adjacent to the opposite side lengths in a right triangle, is the tool for this job. If cotangent of 36 degrees is equal to the adjacent, that would be BC, divided by the opposite, that would be AB, then cotangent of 36 degrees times AB should give us the length of BC. To generalize this, we can say that the adjacent side of the little triangle will always be cotangent of half of one of our central angles times half of our side length. Since our central angle can always be represented by 360 over n, then half of our central angle can be represented as 360 over 2n. This simplifies to 180 over n. Therefore, the side length of BC is S over 2 times cotangent of 180 over n degrees. We now know the sides of our triangle in both general and specific terms. Feel free to pause the video and work out the area of both the little and the larger triangle if you haven't done so already. The area of our little triangle is 1/2 times its base times its height. That would be 1/2 times S over 2 for its height, or side AB, times S over 2 times cotangent of 180 over n degrees. This is equivalent to S squared cotangent of 180 over n degrees all over 8. That is the area of one of our smaller triangles. The area of one of our larger triangles is simply double this area. Multiplying this by 2, we can now pull the 2 out of both the numerator and the denominator, giving us S squared cotangent of 180 over n degrees divided by 4. This is the area of one of our inner triangles. Remember that for any n-gon, we simply have to multiply this area by n to find the area of our polygon. Multiplying this by n, this is our final formula for the area of a regular polygon. I'd like to rewrite this in terms of radians. Simply replace the 180 degrees with pi radians. This will make it easier for us to solve our problem. So let's just do a quick recap here. The reason our formula works is because all regular polygons can be broken up into n isosceles triangles, where n is the number of sides in our given polygon. And what's interesting is that the central angles also depend on n. They're represented by 360 over n degrees, or 2 pi over n radians. We were able to find the area of one of these isosceles triangles by using trigonometric ratio, cotangent. And then we multiplied that area by n, the number of triangles in our polygon, or the number of sides in our polygon. Doing this allowed us to find the area of our polygon. I think that's really cool. It's pretty amazing that any polygon can really just be broken down into triangles. And finding the areas of those triangles wasn't so bad. Let's tweak the general polygon area formula to give us the area of polygons from case A. Remember that in case A, the side of each polygon is given by 1 over n minus 2, where n is the number of sides in that given polygon. All we have to do to tweak the general polygon area formula is to substitute 1 over n minus 2 as S in our formula. This is the result. Let's graph this and see what happens. Here's the graph of our general polygon area formula, tweaked for case A, with the x-axis representing the number of sides of a given polygon from case A, and the y-axis representing the areas of those polygons. Note that the graph begins at n equals 3 because the first polygon from the infinite sequence of polygons from case A is a triangle As you can see, the areas do decrease as we decrease the side lengths. However, they do seem to be leveling out a little bit. We can't prove anything conclusively from a graph, but it does give us a good idea of what to expect. Now remember that this is the graph of the areas of polygons based on side number for case A. What we want to know is whether the sum of these areas converges or diverges. Now, if we can somehow prove that these areas will never get below a certain number, then we would have already proven that the sum of all these areas diverges. Now, why is this? Because if our areas never get lower than a tiny measurable number, adding them together endlessly will give you an immeasurably vast result. After all, even a number as tiny as 1/1,000,000 times a trillion comes out to be 1,000,000. So if we can prove that the areas of irregular polygons stabilize at some non-zero value, then we would have also proven that the sum of the areas of those regular polygons diverges. Let's do that now. So what we'd like to do is to evaluate the limit as n goes to infinity of n cotangent of pi over n over 4n minus 2 squared. Before we find the limit, let's try to rewrite this equation. What we'd like to do is break up the limit of this product into a product of the limits of both of these terms. However, we cannot do that because cotangent of pi over n goes to infinity as n goes to infinity. Since this term has no finite limit, we can't just use the product rule of limits in this case. However, we can apply a quick little trick that will let us use the product rule of limits. We can rewrite cotangent of pi over n as n over pi times pi over n times cotangent of pi over n. If you notice, this did not change the value of our term here, as n over pi times pi over n is just 1. In addition, we can rewrite cotangent of pi over n as 1 over tangent of pi over n, as cotangent is the reciprocal of tangent. Remember that this is still the same equation as the one above. We can combine these two terms on the left. We can now multiply the two terms on the left together to get this new equation. Notice that the term on the right is simply the reciprocal of the derivative of tangent at 0. Remember that the derivative of tangent at 0 is defined as tangent of 0 plus h minus tangent of 0 over h, and it's defined as the limit as h goes to 0. Now if you notice in this case, pi over n is our h, and as n goes to infinity, pi over n goes to 0. So all this fraction here really is a reciprocal of the derivative of tangent at 0, and the derivative of tangent is secant squared of x. So in this case, we have secant squared of 0. Secant of 0 is 1, so secant squared of 0 is still 1. What this means is that our right term has a finite limit of 1 as n goes to infinity. We could use the product rule of limits for this whole limit here as long as our left term also has a finite limit. So let's check that it does right now before we try to apply the product rule. We can expand the parentheses of n minus 2 squared to this. Now that we've expanded our denominator, let's look at what's really going on here. We're looking to find the limit as n goes to infinity of this fraction. One thing we could do is divide all terms in this fraction by n squared. This is what we get. We can use limit rules to simplify this to 1 over 4 pi minus 0 plus 0 by applying the quotient, sum, and difference rules of limits. Therefore, both of our terms have finite limits, which means that we can now use the product rule of limits. And now that we know the limits of both of our factors, this becomes 1 over 4 pi times 1. So the limit of our equation here is 1 over 4 pi. That means the sum of the areas of the polygons from case A goes to infinity. I think that's really interesting, don't you? A million-sided regular polygon, known as a megagon, with sides nearly as small as 1/1,000,000th, has about the same area as a 1,000-sided regular polygon with sides of 1 over 999. That's a big difference in side length, but a very tiny difference in area. I encourage you to pause the video and try to tweak the general polygon area formula for case B. Here is the equation for the area of our polygons from case B. We can rewrite this equation to get the following. And if you notice, this term on the right will tend to 1 as n goes to infinity, and this term on the left will tend to 0 as n goes to infinity. For the denominator is exponential and the numerator is a polynomial. Since the areas don't level off at some non-zero value, the sum could converge. While this doesn't prove that the sum converges, in this case it actually does converge. We will not prove this in this video, but I will show you a graph of the sum of the areas of the polygons in case B. So here you go. Here's the graph of the sum of all of the areas of the polygons in case B. As you can see, the sum does converge to around 0.852. Isn't that cool? You can add all of these shapes, and the sum of their areas will converge to this seemingly random number. So we have our answer now. The sum of the polygon areas in case A diverges, while the sum of the polygon areas in case B converges. Thank you for watching. Please subscribe, like, comment, and share with your friends. Let me know in the comments if you'd like to see a sequel about how the areas of polygons relate to the area of a circle, the circumference of a circle, and the number pi.